Hey guys, today I wanted to talk a little bit more carefully about thinking recursively about sequences and how we can define those. A recursive sequence is any sequence where the formula that you use to find a particular term depends on earlier terms. We often think recursively if you're just thinking 7, 10, 13, 16, I'm sure you can figure out the next number in that list is 19. And you probably did that by saying, well, we're just adding 3 each time, right? We took the last number and we added 3 to it. That sort of thinking is recursive thinking. When you do that, each of those different terms is called an iterate or sometimes an iteration. And the way you could define and write out that sort of thinking is with an expression like this. You would say an is equal to 2 times an minus 1 plus 1. And what this means is if you want the current number, you have to double the previous number and add 1 to it. And so if we have a 2 here, if we want the next number here, this is going to be our previous number doubled. So 2 doubled is 4, plus 1 is 5. And the next number would be, again, this 5 doubled plus 1. So 10 plus 1 is 11. So sometimes instead of writing things in terms of an, sometimes it's written in terms of an plus 1. And so this is the exact same rule, but it's written just a slightly different idea behind it. In fact, you probably heard me saying it. This is the next number is equal to 2 times my current number plus 1. And so if you want to write it that way, you could. Either way, I'm going to take this, double it to get 23. 23 doubled, 46 plus 1 is 47. And 47 doubled plus 1 is 95, I think. And this works great for the next couple of terms, but you can't really use recursive thinking to come up with the 100th number in the list without using some sort of a tool. So let's look at a couple examples. First example, we studied earlier, an arithmetic sequence. Arithmetic sequences are where you add the same thing every single time. And so here, 2 plus 3 is 5, plus 3 is 8, plus 3 is 11, and so forth. If you wanted to define this sequence recursively, what you'd need to do is to tell us what the first number in the list is. That's the 2. And then you need a rule based on the previous numbers. How do we get the next one? And so we would write that by saying n minus 1. And then we would add 3 to it. That's how we get the next one each time. In general, any arithmetic sequence can be written recursively like this. It's simply a matter of stating the first number in the list, and then your rule is always the previous number plus whatever your common difference is. A geometric sequence is similar in the sense that you can define it pretty easily. In general, you define it recursively by saying take your previous number and multiply it by whatever the common ratio is. Here's a specific example. Looks like we're starting with 2 and tripling, then doubling, then tripling. Wait a minute, that doesn't make sense. That's a typo. How about we don't start at 2? How about we start at 6? So 6 doubled becomes 12, doubled 24, and so forth. So we'll start off with a 6, and then our rule each time is going to be to multiply the previous number by 2. So the most famous recursive sequence, and possibly the most famous sequence of all time, is the Fibonacci sequence. Fibonacci sequence, you're told 2 initial values. The first number in the list is 1. The second number is also 1. And then the rule is simply to add the last 2. And so when it says an minus 2, that means look back 2 in the list. This means look back 1 in the list. So when you do that, the first 2 numbers, when you add them together, you get a 2. 1 plus 2 gives us a 3. The next number would be 2 plus 3 is 5. And then 3 plus 5 is 8. And 13, and 21, 34, 55, 89. And these numbers are really popular, really famous. I bet every mathematician can recite a handful of them just off the top of their head. And you've probably seen these too, like literally seen them in nature. These numbers show up all sorts of different places. You pick up a random pine cone or a random flower and you count how many, say, spirals it has on it or how many petals it has on it. Chances are it's going to be one of the numbers here in the Fibonacci sequence. Here, for instance, is an example of a sunflower, and they've counted how many spirals are going in each of those different directions. If you count this way, there are 21 spirals that go all the way around. And if you count the spirals in the other direction, there happens to be 34. I mean, why? It's pretty sweet. Another aspect of the Fibonacci sequence that shows up in a lot of different places is what's called the golden ratio. And you'll see this in art and architecture all over the place. If you look at a pair of these numbers and you divide them, so 21 divided by 13, or 34 divided by 21, or 144 divided by 89, as you go further and further in this list, those numbers get closer and closer to a number that we've called phi or phi. And so our question of the day is simply, what is the ratio between the 100th and the 101st terms? Now, that's a long ways down the list here. And so we're going to have to figure out how can we come up with, how can we define recursive sequences using some sort of a tool to be able to calculate that. So I'll show you a couple different tools that you can use to define sequences recursively. One, it's simply your calculator. It can kind of work with things recursively. In fact, you may have done this before if you've had some sort of boring class and needed to just kind of fiddle some time away. Maybe you started by hitting 1 and hitting enter, and then you wrote +1, and the calculator made it do answer +1. And when you hit enter, what happens is it takes your previous number and adds 1 to it. And so if you keep hitting enter, that's a recursive sequence. It's kind of a boring one, but it is a recursive sequence. Here's one that's a little bit more interesting, I suppose, but you can start by hitting 5 and enter. And then if you wanted to triple this number and subtract 4 from it each time, you could type 3 and second answer -4. So let's see if these numbers are right. 5 tripled is 15, -4 gives us 11. 11 tripled is 33, -4 gives us 29, and so on and so on. So that's one way to work with recursive sequences. It's not maybe the best because you have to count as you're hitting enter on your calculator and make sure that you keep track of it. So if I wanted to find the 100th number in the list, take 100 button pushes and counting to 100, and I wouldn't want to miscount or anything like that. So I want to show you a better tool. Another thing that you can do on a calculator is to use sequence mode. And so if you want to use sequence mode, you'll have to press mode and switch from function, which is probably what you're in, although maybe if you were in my pre-calc class, you might still be in polar mode from our graphing unit. But anyway, switch over to sequence mode. And if you do that, then when you press the y equals screen, instead of seeing normal y equals equations, you'll see u equals and v equals and w equals and so forth. And so what you'll want to do then is type a formula in. This is that sequence where you are tripling a number and adding 1 to it. And so starting with 5, tripling a number and adding 1, you can get the u and the v and the w. Second 7, second 8, second 9 are the u and the v and the w. And so you can type those in. To get the n is if you press the X and T and theta and n button, when you're in sequence mode, you'll get an n. So anyway, you type in formulas like that, and then if you go to table, which is second graph, so instead of graph, hit second graph, then you'll see a list of all the different values in there, and you can scroll through that list and jump to the 100th number if you want. do want to show you one more tool that you can use to work with recursive sequences, and it has nothing to do with your calculator. This is a spreadsheet, so this sort of thing will work with any table, Google Sheets, Excel, numbers, and so forth. If you want to define a sequence recursively, you'll have to start off with one number in a cell, and then you'll use an equals to do it, and then drag that formula down. So if we wanted to do, say, the Fibonacci sequence, or why don't we just start with the simple counting sequence? If I have 1, instead of typing 2 and 3 and 4 and so forth, we can save ourselves a little bit of time by using a recursive rule. I want this number to be 1 more than the number above it. So I'm going to type equals and click on this box and then add 1. And when you hit enter, notice how it became 2. The really important thing is to find the little fill handle that's down here and drag that. Once you do that, it'll drag that formula into all the others. And notice each one of these was found automatically. Now, suppose I wanted to find the Fibonacci sequence this way. Remember, I need to give it the first 2 numbers on the list. So first number was 1, and the second number was also a 1. And now what I want to do is define this using a formula. So I'm going to type equals, and I'm going to go to this box and add this box. And it calculated it automatically. And if I drag this down, be sure to click in the square that has the formula in it, and drag that down, all these other numbers will calculate automatically. And so I don't have a big enough table here to go all the way down to 100, but you could easily do that in a spreadsheet, right? Let's look at finally the ratios between each of these different terms. And so to find a ratio, what I'm going to do is, again, an equal sign. I'm going to want to divide. I want to divide 1 by 1, and 2 by 1, and 5 by 3, and eventually 34 by 21. So I want to divide this cell by the cell above it. And so that first ratio is 1. If I drag this down, the next ratio should be 2, because 2 divided by 1 is 2, and then 3 divided by 2 is 1.5. And notice as I go further and further down this list, these numbers are zeroing in on 1.61803. In fact, it only takes us 14 numbers, and we already have the first 5 digits of phi. And so if you did this on a spreadsheet, went all the way down to the 100th number in the list, then you could find the answer that way too. All right, I want to show you one last example using recursive sequences and spreadsheets, and kind of an advanced technique, but a very useful one. For this example, we're going to refer to my house. So I don't know the exact numbers, but right now we owe close to $150,000 on it. And for monthly payment, I think we're paying $1,600 a month. And our interest rate is somewhere around 3%. And so 3% is 0.03. And what I want to do is produce a table that has how much my amount is after every month. And so the way that that works is I will start by taking the current amount and multiplying it by the interest rate so that I know how much interest gets added to my debt each month. So I'll do that. I don't want to type 0.03 in there, but I want to refer to the cell here. And so I'll click on that. This is a monthly payment calculation, and this is an annual interest rate. So I do need to divide that by 12. And if I were to just stop right now, what's produced is the amount that has to be added to my debt. And so let me add the previous number to this. And then I am making monthly payments on it, and so I'm going to subtract what my monthly payment is. And if I hit enter, here would be what I'd have after 1 month. And if I just tried to drag this formula down, I start to get some errors. And the reason I start to get some errors is because the cells that I'm referring to, as you can see, are moving down with me. And I don't want them to. I always want to refer to this cell, B3, whenever I'm using that monthly payment. And same thing, I always want to refer to B5 when I'm calculating the interest rate. And so to make that change, what you need to do is anchor those cells, and you anchor them by typing in a $ in front of the cell name. And so instead of just B5, I'm going to type a $ in front of the B and a $ in front of the 5. And I'll do the same thing with the monthly payment that was here at the end. I'll put $ in front of those. So now you'll see that when I drag that down, the cells that it's referring to are always those two up there. By setting it up in a table like this, then you can play around with the numbers and say, well, what if I paid off, what if I could afford $2,400 a month? And all those numbers recalculate. And if I could scroll down to the bottom and see, maybe now I could pay it off in 12 years instead of 15 or something like that. Anyway, I hope this has been enlightening to you. Let me know if you have any questions about setting up recursive sequences on either the calculator or the computer. And I'll catch you in the next video.